the schedule on the long sheet of paper, if you notice on the, what would be the back side of it, there's a space down at the bottom. And what I meant to write in there and forgot to write is how I graded this. So what this says right here, you could write in that space if you want to have it on there. So it's what you would expect from how I've always done things, but I should have got that written in there. So you can write it in.
Well, it's the same as last time, right?
Yeah, yeah.
Oh, okay.
Yeah, so if you don't care, don't worry about it, but.
No,
But if you care,
It's my third class.
you could write it in where on the one side, there's a space, you see test, number, name, date of distribution, then there's some space down there, and if you want to have what I should have written in that space, then you can write the homework and the 4 tests and the O and A thing. Any way you want to write it. So the sheet of paper that has the 2 colors on it is quite interesting because usually we represent our vectors as arrows, and we use however the arrow points for the sense of direction and the length of the arrow for the magnitude. And that's the normal way that people work with vectors in physics or engineering or math. But it's interesting that there are other ways that you could represent a vector quantity where you have to represent a sense of direction and a magnitude in some way. And so one way that you can do it is how it was done in this history book that I've copied here. And in that, you're using the width of the drawing to represent the magnitude, and then how things point for the sense of direction. And if you notice what it is, it's copied from a book that was originally written in French, and it's talking about Napoleon's invasion of Russia, and what you have going east, and going from left to right, is the vector that represents the French army by position and various battles by dates there and little notes. And so you see how big an army it was to start with by the width, and then on the right they get to Moscow, okay? And you see how much is left of it by the time they get there by comparing the width. And then reasonably enough, they're using the black for the trip home. And you see more and more freeze and so on. And you see how many get back to Paris.
So that's a drop in population?
Well, of the French army, yes. Yeah. Yeah, they started out with something over 400,000. And I think it says in there what they got back with.
So 10.
Yeah, and so on. And, but it shows an awful lot of information in a graph, because you can see where they've had various battles with the Russians, and that the vector is slimmer, shall we say, as after that. So it's the vector idea is that you're trying to represent something that has both a magnitude and a sense of direction to it. And the book there is one way that people have done it. Another way you can do it is with a map. For example, if you're trying to, if you look in the Thomas book, there's a picture in the start, I guess. I don't think it's chapter 12 where we are. I think it's in chapter 16. But if you go through your loose leaf notes to the start of chapter 16, where they're talking about what they call a vector field, they're talking about wind speed, for example. And so there is a map of the Earth, and then superimposed on that are arrows. So the direction of the arrow will show which way the wind is blowing throughout the world on a particular day at a particular time. And then the colored background, there are outlines of the countries, so you can see if you're in South America or Africa or here or wherever. But the colored background would be the magnitude. So you can get a sense of where there's a storm by the arrows kind of going in a circle, and essentially how hard the wind is blowing by the various colors in the color scheme. So you can represent vectors that way. But for the purposes of doing things like statics problems, which are over there under the clock, and for the purposes of the math in chapter 12, we'll think of drawing arrows where the length of the arrow is proportional to the magnitude, say, of a force, and how the arrow points is the direction. And that's the point of view in the notes that are on the long paper. So we can start here. We think of a directed line segment from A to B, where A and B are points in the plane, and thinking of the line segment, since it's directed, there's a sense of tail and tip. So A, if you write A, B, it's from the letter at the left to the letter at the right, and point A and point B. And in the book, a vector is represented with boldface type. If you look at how your book is printed, I don't have boldface handwriting, so what we do is we put a line over it to indicate that it's vector and not a number, say. Then the magnitude, which would be the length of the arrow, or equivalently, it would have been the width in this picture, or it would be the color if you had a color scheme background. The magnitude then would be represented this way and is the length. And you can either use the single bar vertically on each side like you do with absolute value, or you can use double bar. Depends on whose book you're in and whose class you're in. So two directed segments, A, B, and C, D, are equivalent, and this wiggle thing reads equivalent when they point the same way along a line, script letter L, or along parallel lines, and when the magnitudes are equal. See, it's more than just simply saying that they're pointing along the same line, because they could be different lengths, of course. And it's more than just saying they have the same length, because they could point in different directions.
I forget what that squiggly line is, but does that mean that, are they roughly equivalent, or are they equivalent?
No. Often in other classes and in other work, it does mean approximately, roughly equivalent. But
Okay.
here, I'm using it as equivalent in this sense, that
Okay,
they're directed alike and they have the same length.
okay,
So through each point then in the plane, we can find a directed line segment, CD, with tail at a point P, where CD is equivalent to AB for any given AB. Just a minute here. So, so the vector that I write as AB is the set or collection, it's not just the one single arrow is what I'm trying to get at. It's the set of all directed segments that could be called C to D, where C and D are any 2 points that are equivalent to AB. And again, equivalent to means then that wherever you are at point C, you place the tail of that arrow there, and it will be the same length as AB and point the same way. So you don't have just the one single arrow. Like that. You also have another one here. And another one here. Another one there, and so on. There are infinitely many. They're not perfectly drawn, of course, but they're all supposed to look parallel to you, to the AB, and have approximately the same length. Here's the candy
You're
lady.
missing students.
Yeah, I don't know where they went.
Yeah.
What'd you do with them? Let's make them charge.
I don't know, it happens every time.
Well,
For them. Okay, well, welcome. We just need to go over just a couple of things. The last day to drop this class with a full refund will be next Friday. Not that anybody's gonna drop it, but it's good that you know that. They do ask that you do not park in the visitor parking lot, even if you're a Micron employee. They will come and get me and make me come and get you out of class and have you move your car. You can park any place but the visitor parking lot. Any place else is just fine. Be sure and not go through any doors except the front one because the alarms go off. There may be a fire alarm at some point. They usually tell me if there's gonna be one, so I have a warning. Micron employees, raise your hands, follow them. If there's a drill, just go with them. We have to all go outside, and then we come back in. We usually know about it, so it's not too big of a deal. The thing is so loud, you can't stay in the building even if you want to. It's just awful.
Yes.
Yeah, it's very loud.
It really
just
is.
ear piercing,
Yeah.
yeah.
you
And
see
it's right there,
Right there.
yeah, so it's just, yeah. If there is any kind of an emergency, we do not call 911 here, we call 66611, there are phones right outside. Most of the time, there's enough Micron people around who can handle it. We have very good EMTs and fire people who come immediately. We don't have a lot of those happen here. A couple of years ago, in one of the engineering 120 labs, a guy cut his finger with an X-Acto knife. They were here and bandaged him up so fast, and it took 3 months to do all the paperwork for him.
Of course.
It was a Boise State class,
Yeah.
so between Boise State's paperwork and Micron's paperwork, it was, please don't cut your finger. It was a nightmare. This class is twice a week. It's important to come every day if you can. We have a tradition at Micron, we start with candy, because a chocolate high makes you think better. And technically it's a vegetable, because it grows on a tree. So we like to have. Huh?
I like that validation.
Yeah,
Yeah.
yeah. It's health food because it's a vegetable, grows on a tree. We're happy to have you be here. We hope you come back tomorrow. It really hurts my feelings if people don't come back the second day. I do take it personally, so just remember that. So does Dr. Maloof. We take it
Yeah,
very personally.
hurts my feelings.
That's right, it hurts our feelings. We don't like it when people don't come back. So, I'm gonna leave this here in case some more people come, and we will see what happens. I'm gonna try to round up more, but we'll see. Thank you all for coming and have fun. Math is good, huh? Yeah,
Math is great.
yeah, yeah, it's great.
So anyway, we have this idea of a set, or you can call it an equivalence class of arrows that are all directed alike and all the same length. So these will represent forces or velocities, physical quantities that require a sense of magnitude and direction to specify them, which of course is how they say it in the physics class. The point of the equivalence class concept, which is a math department concept, which is a little more sophisticated, is that it's the justification when you're working a force problem, a statics problem, such as those over there under the clock, for saying you can put your arrow any place that it's convenient in analyzing the problem. Because as long as the arrow points a specified way and has a specified length corresponding to the magnitude of a force, then you have fully specified it regardless of where you put its tail. So you put it wherever it's appropriate to the particular problem you have. So the vector v then, again, the bar over the letter means boldface type. If you look at how your book is printed, you see they're in boldface type. Is actually then not just one arrow with a given length and for its magnitude, but it really is the entire equivalence class of infinitely many arrows, which means that no matter what point it is in the plane, say, there is an arrow for which you can put the tail right there. And it'll point however all the vectors point in this set, and it will have the length, in other words, the magnitude of the force or velocity or acceleration that all of them have. So when you need one, when you're adding vectors, for example, as I'm doing over here, you put down one arrow and then you need one that will have its tail right at the tip of that first one. There is one there because the second arrow, looking at the red and then the green, where I'm going to add vectors by forming the triangle, I have this vector first, and then at this tip of U, of the red one, I want one called V that I'm going to add to U, say, if I'm trying to construct U plus V. Well, the reason that I can always do this is that the equivalence class V of green arrows that look like this one is not just this one arrow, there's the whole plane full of them. So there is one with its tail right at the nose of this one, just like dogs, where you have the nose of the one dog at the tail of the next dog. Well, dogs do this, as you know. Okay, so that's essentially what I'm saying here. We have two equivalent rules then, the parallelogram rule and the triangle rule for adding and subtracting vectors geometrically. We don't ordinarily work problems geometrically because it's easier to use numbers, but the concept of that you can add vectors geometrically and subtract them is important to understand how we work with vectors in analyzing statics problems, say in physics or engineering, things like that. So rather than write out the word parallelogram, I draw the little hieroglyph, or triangle, I draw this one. So if you want to construct U plus V, select a segment AB from the vector U. Now when I say the vector U, I mean this whole infinite class of arrows that are all pointed alike and all the same length, what you could call a vector field. The language in the book is to say vector field then. And so that would be in my picture. Here's the triangle rule picture, and here I'm doing the same addition problem with the parallelogram rule. So I'm doing the same thing twice here to show that you can do it either way. So I select U. Then I select segment BC. So U, the segment from U that I selected is AB. And whatever point A it is, there is an arrow from the infinite set or vector field U that I could select with its tail at A, because there's an arrow with its tail any place you want to be, because it's a whole infinite set. So then B is at the tip of this one when its tail is at A, and then that defines segment AB. Then at this point B, for whatever representative I want from the infinite set V, I can get one where its tail will be at B, because there is one with its tail any place. And so then I draw this from B to C, and then in the triangle rule for addition, the third side of the triangle is my vector sum. So this would be vector AC, which I'd call U plus V. If I'm doing it with the parallelogram rule, I start out the same way and form the two sides of my triangle like this, and I also complete the parallelogram. So then another representative of vector field or equivalence class V is the one for which the tail is back here at A, and another representative of vector field or equivalence class U is the one that has its tip down here. If I wanted to, I could have called this point D, and so it would, you could say it has its tail at D. And so I have the parallelogram, as you see. Well, then your vector sum is the diagonal of the parallelogram that is tail to tail with U and V, if you've placed them tail to tail. And the other diagonal will represent the differences. The advantage of the parallelogram rule over the triangle rule is it also lets you display vector differences. So you see there are two arrows here, a blue one and an orange one. And the blue one has its tail down here. I probably should actually write the letter D. So the blue one has its tail at D, and the tip is up here at B. So it's head-to-head with U. So that one then is U minus V. It's head-to-head with U. And the other one, V minus U, is the other diagonal that's head-to-head with vector V. And so that's the vector from B to D. So you notice that what we're saying is that the one of them is the negative of the other one. They're both the same length arrow, but they're directed opposite. They're directed along the same line, which is where your diagonal is, but pointed opposite. So then in the triangle rule, the sum is the third side of the triangle. So if all you're trying to do is draw the sum, you could do this. The parallelogram rule, the sum is the diagonal here that's tail to tail with the two vectors you're adding, if you place them tail to tail. And then the differences, the two, are as I've already written. So you want the parallelogram rule if you want to draw the vector differences. So scalars then are real numbers as opposed to vectors where there is this sense of direction as well as magnitude. You can multiply a vector, again, remember I put a line on it if I'm doing handwriting, and it's boldface type if it's printed in the book. You can multiply a vector by a scalar to form a new vector. So if C is 2, then this would be 2V, and it's going to point like V but be twice as long, and so on. If C is positive, then CV is directed like V, and if it's negative, it's opposite, like minus 1 times the blue one would be the orange one, or you can say it the other way around, of course. If the scalar C is 0, then 0 times V is the 0 vector. So in the book, that's a 0 in boldface type. In your handwriting, it's a 0 with a line over it. So it has magnitude 0, and you do not specify the direction. Could point in any direction. You do not define division of vectors. We never do that, this class or anybody else's. But we do have two senses in which you can multiply vectors. One is called the dot product, which is tomorrow's class, and one is called the cross product, which we'll do a week from today. Those are the sections 12.3 and 12.4. You may very likely have heard the terminology from other people's classes, and you may perhaps know how to do them from other people's classes, but we'll talk about dot product tomorrow and cross product next week as if you didn't know how. Yes?
Why the division is undefined?
Well, because when you talk about division, for example, you say 6 divided by 2 is 3, right? Because you can check your work, 2 times 3 gives you 6. But you see, we have two different senses of multiplication. So in the equivalent sense, if you wanted to say vector V divided by vector U is a vector W because U times W gives V, well, in what sense of multiplication? You have more than one way you multiply vectors, so you can't have a single answer to it. So whenever you would have a process for which there isn't a single way to check, we say it's undefined in mathematics. It's kind of the same thing as why division by zero is undefined. Because if you wanted to say 6 divided by 0 is 2, because 2 times 0 is 6, you can see what the trouble is. When you try and do the multiplication, it's not going to get you back. So we never do it. Vectors obey an algebra. Actually, the word algebra in quotes, an algebra is a technical term in mathematics in the sense that there have to be operations like plus and times, things like that, that will obey a set of requirements or rules. So suppose these are any 3 vectors, and then C and D are scalars, real numbers, in other words. So we have what is called the associative law, that if you're applying the operation plus to the things that you call your vectors, you can apply the operation to 3 of them in any order. You can do u plus v first, and then that's a new vector that you add to w. Remember that vector addition means you can either do this or you can do this. So I could take u and v and construct this one, and then add this one to another vector w with another triangle here or another parallelogram. So I can do it in any order. I can do u plus v first, or I can do the v plus w first, and then add that to the u. If I'm working with multiplying by 2 numbers, I can multiply the numbers first, and then that number times v, or I can take one number times v, that's a new vector called d times v, and then multiply that by the other number. So both of these are what you call the associative law. The commutative law says you can write the vectors in either order if you're applying plus. These are familiar properties because our number system does all this, but when you're talking of addition, subtraction, operation in a different sense than numbers, there's the issue of, do the things that you're calling your vectors do this in the same way? Then you could add your 2 numbers first, and you could also and then take that times the vector u, or you could take one of the numbers times u and the other one times v, and then add those 2 vectors. Either way works. 1 times the vector is the vector, which you would think that's how we use the number 1, but when you're doing a different kind of addition than you do for numbers, after all, you're doing this kind of addition and this kind of subtraction, you have to say whether you can really do that the same. And if you multiply by 0, you get the 0 vector. If you multiply by -1, you get your vector turned in the opposite direction, but along the same line of action. So when you write u minus v, it's the same as you took v, turned it around, and then added, as you could with a triangle rule. And so u minus v means this, so it means u plus the vector minus v. So finally, we get to the component concept, which is probably familiar to you from other people's classes that work with vectors. So that lets us relate the algebraic and geometric properties, and the geometric properties are important to form the concept of what you're doing, and the algebraic properties are important for actually working specific problems efficiently and not by drawing pictures. So, as you know from your engineering classes, we introduce the unit vectors I, J, and K if we're in 3 dimensions. This can be boldface type, or you can put a little hat on it. The little hat means that it's length 1, unit vector. And it's the unit vector directed along the positive x-axis, as a lot of you probably know. And J is the unit vector directed like the positive y-axis, and K like the positive z-axis. So what's the z-axis idea, which goes back to the section 12.1. So if you get over here in the corner where you can do something that's 3-dimensional, usually what we do is we think of the plane of the floor as the XY plane if you're working in 3 dimensions. So then your x-axis might be the seam along here between the different colors of carpet, which I think all of you can see. And then the same way the y-axis could be the seam of different colors of carpet going that way. And then the z-axis would be up like the column here. Unfortunately, they didn't build the room with the column there for just to please me with my mathematical model, but you see the idea. So then positive z would be upward above the floor and negative would be downward. So then I have the unit vectors in those 3 directions. And so the key result of all this is that you can write a vector in the xy plane as a linear combination. V is a times I, the unit vector I pointing along the x-axis, and B steps, say, in the direction of unit vector J along the y-axis of I and J. So we call those the components of V. We can also use the angle brackets, which is what I will use primarily, to write the vector in component form. So something written like this means the same as that. But this is actually a handier way to write it. This is more likely what you see the engineers doing. So for a directed segment then, A to B, your tail is at the point x, y, x-coordinate, y-coordinate that go with point A. So I'm calling the x-coordinate x sub A, the y-coordinate y sub A. And the tip is at the point corresponding to B, where the coordinates are x sub B and y sub B. So in general, this is a different pair of numbers from that pair of numbers. And of course, if the line were horizontal, the y numbers would be the same, and if it were vertical, the x numbers would be the same. Okay, so the way then that you represent a vector in component form, when it is from point A, for which you have the coordinates, to point B, for which you have the coordinates, is like this. You take the right-hand x minus the left-hand x, and then that difference would be the letter A, that would be here. And then you take the right-hand y minus the left-hand y, and that difference would be the b. It would be there, or I have it right here. So you can get the a and the b to write the vector with the angle brackets, or if you prefer, using the I and j, when you know the location of the tail and when you know the location of the tip. So then you can write your vector either this way, as engineers do, or this way, as the math department does. And I think the physics department does this sometimes and that sometimes, depends on whose class it is and what book it is. I've certainly seen people do it both ways. I don't care which you do, but you should understand that you can do it either way. So if you have V as AB and W as CD, then if you're adding the vectors, what you do is you add the like components. So it's the vector A plus C, then B plus D. And it's the same whether you use the angle brackets or say A plus B, A plus C I, and B plus D J. But notice that that's more writing, because you really have to put parentheses around the A plus C times I, and then plus, and then parentheses around the B plus D, and then times J. So this is really a more efficient way to write vectors. So to add vectors, you add like components, is what the bottom line is. Similarly, if you want to multiply by a scalar, the two vectors, a vector, say AB, then you multiply each component by that scalar. If you want to multiply by 0, you multiply each component by 0, so then you have the vector 0, 0 in the plane using angle brackets. In other words, 0i plus 0j, if you prefer. So the vector v is the 0 vector if and only if both of the components are 0. So then finally the length, you see, you're thinking of a law of Pythagoras sort of situation. Here is your vector v as an arrow, and when you say it's a b in component form, you mean that the length a would go this way in forming the right triangle, and the length b would go like this, and then you can think of your law of Pythagoras. A squared plus b squared is the squared length. So the length is written, I said this a few minutes ago, either with a single vertical line like this, the way you do absolute value, or to distinguish away from absolute value, use a double line, which is okay, but more labor. And so then you will have, from the law of Pythagoras, square root of a squared plus b squared. So the direction vector for V is a unit vector where the length of the unit vector is 1. That's why you call it a unit vector. And so then the direction vector has length 1, and to get the sense of direction, it's V over length V. So this is a vector then. It has length 1 because you're dividing by its length, and it points the same way V does because it is the scalar 1 over length V times V. And if you multiply by a scalar that's a positive number, your two vectors are going to point the same way. So this unit vector that is pointing like V is called the direction of V, and it's an important concept, actually. So if you're given a vector and you're asked to find the direction for that vector, that has a technical meaning. It means you take the length of the vector you're given, then divide the vector by that, and that gets you a new vector pointed like the one you started with, but length 1. And that new one is called the direction of the one you started with. So these are the general rules of vector algebra, if you want to say it that way. So then we can come over here, and these are homework problems if you were doing the homework that's the written problems in the book. And there'd be some if you're doing it instead with the My Math Lab system, there'll be some statics problems in those that would be like them. For the benefit of all of these people have taken classes from me, so they sort of know what I'm going to say next, so this is really for your benefit. You can do the homework My Math Lab if you like that, or you can do the problems that are on the long sheet of paper, which refer to the problems in the book, and do them handwritten if you'd rather do that. And you can do the handwritten, say for section 12.1, and you could do My Math Lab for 12.2, things like that. You don't have to do them all alike. But any one section you're in, complete it all one way or all the other way. It's too hard to assign credit to some My Math Lab and some handwritten. And so the long sheet of paper refers to what the handwritten assignments would be each class, and will tell you also what sections are covered. And what I do on the board for my examples is some of the handwritten homework. So if you're doing it handwritten, and I've done them, like I'm going to do 45, 6, and 7, even so, if it's on the long sheet of paper to do 45, 6, and 7, write them out and turn them in, basically copying what I've done, I admit. Amanda grades the homework, and I don't tell her which ones I do in class, so she would be looking for one of those three, I'm sure. You see what I'm saying? Okay. So, what we call statics problems then in engineering and physics are based on Sir Isaac Newton's idea that the sum of force vectors would be what we call the resultant vector, and it's proportional to any acceleration that the object will have to which these vectors apply. So if there is no acceleration, which means statics, that means the vector sum of the forces has to be 0, meaning the 0 vector. You notice I was careful and put the line over the zero. So if you're working vectors in the plane, which these problems are, the statics problems means essentially that the sum of the x components will be zero and the sum of the y components will be zero. Because if there's a sum that's not zero, then there is a resultant force, and if there is a force, there has to be an acceleration. So a useful result here is this direction vector idea that I just tried to address at the far end of the room. If you have a unit vector, u, remember the little hat on it means its length is 1. At an angle theta with the positive x-axis, then the way you can always represent a unit vector that's at an angle theta is cosine theta for your x component, sine theta for your y component. So we can write any force then that's at direction theta with positive x-axis as F times, as magnitude of the force, I'm using the single bars for the magnitude, times this unit vector. In other words, magnitude of the force cosine magnitude of the force sine. Our rules say that this is the same as if you put this number there and there. So if you look at section 12.2, problem 45, they show you a sketch in the book. Looks like my picture here. So I have two wires or cables suspending a weight, and they're attached to a horizontal frame up here where the stick is. And in problem 45, this weight is 100 newtons. Well, how much is that? It's, newton's about 4 ounces if you work it out. It's, there's an exact decimal, of course, it's 0.224 pounds or some such. So 100 of them is about 22.4 pounds. So it's a weight, but it isn't a horrific weight. Okay, so that of course is a force, gravitational force pulling down like my arrow, all right? And it's suspended there, nothing is moving, so that means then you have a problem in statics, and that this force is balanced by the vertical components from these two forces, F1 and F2, and it also doesn't move side to side, so it also means that the horizontal component from this one pulling toward me balances the component from that one pulling that one. So if you have a problem like this and you measure around from the positive x-axis, it would be over here, this angle theta, then whatever the angle would be, such as, say, 150 degrees measured from pointing like that, you can say that your force is its magnitude times cosine of the angle, comma, sine of the angle. And then when the angle is more than 90 degrees, you have to use your trig identities to get the exact values. But you can always do this, no matter whether it's an angle that's second quadrant or third quadrant. So for example, the force pulling down is third quadrant. The theta around to there is 270 degrees. And then your cosine is 0 and your sine is -1. So that'll get you that the force here is actually -100 J if you're doing it IJ. You can, if you prefer the I and J, instead of saying angle brackets, you could say here magnitude of F times I cosine theta plus J sine theta. So then thinking about your X components, you're going to have the magnitude of F1 cosine of 150 degrees plus the magnitude of F2 cosine of 45 degrees. And that total is 0 because you don't have a net force right or left. And then for your cosine of 150 degrees, it's the same as minus the cosine of 30 degrees, because your second quadrant angle has a negative cosine. So you're saying minus magnitude F1 cosine 30 plus cosine 45, magnitude F2 is 0. In the same way for the Y components, you have the two that are pulling upward, magnitude F1 sine of 150 degrees, which is the same as sine 30, plus magnitude F2 sine 45, and then you have the third force, which is angle of 270 degrees. You see it here in the red. And so 100 sine of 270 degrees, which is -1, equals 0. So simplifying to 30, 45, and the sine 270 to -1, you have that. If you preferred, you see, you could say that the two components pulling up, which are this and this, equals the one pulling down by moving this across. That is certainly a way a lot of people would do it, that you'd say, well, if it's statics, what's pulling to the right equals what's pulling to the left, and what's pulling up equals what's pulling down. You get that same thing out of these if you move the terms across. But I was trying to do it in a consistent way of writing all my vectors as magnitude times these direction vectors for the different angles, and then saying the vector sum of all these vectors is 0. So whatever you want, then your sine 30 is a half, and your sine 45 is root 2 over 2. And so this equation is the same as if you took the 100 across. So finally, what you get is two equations and two unknowns. So this is the vertical one, where I've moved the 100 across, and this is the horizontal. And then if you notice, this is the same thing. So if you take this line minus that one, then what you have is those cancel. You have this plus this, when you subtract, equals the 100. And then if you want to multiply by 2, you can. And then you can divide 200 by 1 plus root 3, and you get that many newtons. So that's, this part is math 25, I guess. And after you know the F1, you can go back and get the F2, because, for example, here it'd be the easiest, take this across, and then root 3 over 2 times this would be divided by root 2 over 2. So what I did is I did my work like this, and you get approximately 90 newtons. Drink some more water here. Look at that for a second. So as I told the rest of the class before you got here, on my long sheet of paper where I have what we're doing, everything, I forgot to write how I'm actually grading, so you could copy that if you wanted on your long sheet of paper. There's one side where there's a space on the paper where I forgot to write that. So notice that the outcome and assessment test is the 2 days, and it's not the 2 days of the finals, the official finals week. It's the 2 before that, the week before that. So it's the, what is it, December 8th and 9th, not the next week. So you get this one done before you have to do finals in the other classes, which is helpful, I think. Meanwhile, look at problem 46. And again, if you have your book, you can see the picture of it. So these are 3 problems, they're all the same idea. You have an angle alpha, which is unknown in this problem. You have this angle, you're told, is 60 degrees. You have the 50 newtons, which is about 11 pounds pulling down, and you're told the magnitude of the force, F1, is 35. So, you see, with your alpha unknown, the angle that I've marked with blue is actually 180 degrees minus alpha. And if you use your trig identities, that's the same as minus cosine of alpha, where alpha is this acute angle that's unknown. So you have 35 minus cosine alpha, comma, sine alpha. And with F2, you're told its magnet, you have an unknown magnitude, but you're told your angles are 60 degrees. So F2 is the unknown magnitude, then cosine 60, sine 60. And so your side to side, or your horizontal or x components, are the minus 35 cosine alpha plus the one from F2, magnitude F2 times a half equals 0, or if you prefer, this equals that. And your vertical components are the 35 sine alpha, that's this one, the root 3 over 2, the sine 60 degrees, magnitude F2, that's this one, and then the 50 down, so minus 50 equals 0. Again, this vector, if you want to write it with the direction angles, is 50 sine of 270, which is the minus 1. And so then what I did is I took row 1 up here and multiplied it by minus square root 3, which gave me 35 root 3 cosine minus root 3 over 2 magnitude F2 equals 0. And then I copied row 2 underneath it. So now you see I have minus and plus the same thing. So I'm eliminating one variable. So I have this plus that equals 50, which is what I have here. And so then I'm solving for root 3 cosine. So I'm taking the 35 sine across and dividing by the 35. And then 50 over 35 is 10 over 7, and that 35 cancels with that one. So I have 10 over 7 minus sine alpha. So then I am squaring both sides. I'm squaring root 3 cosine, which gives me 3 cosine square, and I'm squaring this out like FOIL. So I have the 3 terms. And then I'm replacing the cosine square with 1 minus sine square. So 3 times that is what's here. And I'm let's see. So I have the 3 times 1 minus sine square equals what I got when I squared this out over here, which was the 100 over 49, the 20 over 7 sine, and the sine square. So then what I've done on this side is get a common denominator with these. So 7 top and bottom gives me the 140 over 49, and then I have 49 over 49. So then I multiply through by the 49. 3 times 49 is the 147. So what I'm doing, of course, is solving a trigonometric equation. This is what you do if you take Math 144 or Math 147, those trigonometric equation problems. And I had to first do the trig identity, replacing the cosine square with sine square, so that my equation here involves the same unknown, which is sine of the angle. So the problem here is not really so much with the vectors or with calculus. It's actually a Math 144 problem, which a 144 student would think is a pretty hard problem. And so then you collect all your terms, and that gives you this. And then you use your quadratic formula on it, and that gets you this. And so finally, your sine is written this way, and the angle alpha is positive, so you want the positive square root. See, 6 root 2 is bigger than 5, so if you took the negative, your sine would be negative. And you're talking about a problem with an acute angle. You can see that the alpha is less than 90 degrees, so you don't want something where the sine is negative, which would be more than 180 degrees. So that tells you to take the positive square root from your quadratic formula, and when you do that, you get 74.42 degrees. And after you get that, you know from this one that a half magnitude F2 is 35 cosine. So you take this angle and take its cosine, that gets you here, and then you get this many newtons. So that problem has quite a lot in it, in that you're using this idea from statics of the balanced force vectors to get your two equations. Then you have to handle the two equations and two unknowns to eliminate, as I've done it, the magnitude of F2 and get your trigonometric equation. Then you have to do that with substitution of a trig identity and then the quadratic formula, and finally realize that you can only use the solution with the plus sign and get your angle, and then after all that, get your magnitude of the other force. Okay, the last one is a little easier. In this one, in 47, if you look at the pictures in your book, they tell you the angles 40 and 35 degrees, and you have one of the force magnitudes, this one. You want that force and this one. So what you have is that the F2, the force pulling off to the right, is its magnitude, which you have cosine and then sine. Okay, the one pulling to the left is the unknown magnitude, and is your angle again coming around like this. Is the 140 degrees, and so that means that with your cosine of 140, it's minus cosine 40, which is why the minus sign in cosine 40 degrees. And then for your vertical component, you would have the sine of 40 degrees. So then your statics give you that component to the left plus this one to the right equals 0, and so you can actually solve right here. You don't have to solve this as two equations and two unknowns, because this is the only unknown. So then you have the 100 cosine 35 over the cosine 40, and you get your answer there for magnitude F1. Then separately on the verticals, you have the magnitude F1 sine 40, and now you know this number goes there, plus the 100 sine of 35 degrees, and then that's the W. And so you put in your number here and do your work, and you get this. So as I said, the third one is comparatively easy. Of the three problems, I think the hardest one is the second one there, and the hardest part of it is actually solving the trigonometric equation. Well, let's take a minute before we go here and look at the maple. That everybody should have this. And and the other thing we should do is the sign-up sheets. What I have with the maple in the section 12.1, what they're trying to do is introduce the concept of a figure in 3 dimensions, which in general will be a surface. So if you're looking at something like the first one that I have, which is problem 1 in 12.1, what they want you to do is make a sketch of the vertical line that I have. And so Maple will draw three-dimensional graphs. The command with the space curve for a curve, and you see what it is in the brackets there. Those are like the math department's angle brackets, but if you're using Maple, you use the square brackets. So the 2 would refer to the x. So this is a line where x is 2, y is 3, and then z is your variable. So you could type the letter z if you wanted, where I use t. Generally, you use t to indicate that it's something where you can set limits as on a parameter, as it's called, on the variable. And the formula in terms of t is the formula the problem gives. So the problem as given would be to draw the line where x is 2, y is 3, and z is variable, z. So you have to pick out the limits for Maple, how far are you going to go in that direction. So the minus 20 to 40 that I used is entirely arbitrary. You just have to decide something before it'll draw it. And whatever you choose will determine how far vertically that black line will go. And then you can choose your axes. Normal would be what you see in my picture. You see the x-axis is coming out in front. The y-axis is going left and right. And the z-axis, you can see the scale there. You can see where it's minus 20 on the vertical up to 40. So the graph is a vertical line segment like that. Now, by contrast with a surface, they may define the surface as an equation, like the second example. See, if you define the equation, if you use an equation to define your surface, like x squared plus y squared plus z squared is a number, that's a sphere or a portion of a sphere with center at the origin. And so when you're defining your curve as a function, you use space curve and the vector and the parameter. When you're defining your surface as an equation, instead of plot, you use implicit plot. You use plot for functions, implicit plot for things defined as equations. Then you type in your equation. So you see I've used the set braces because I'm defining a set of two things. I'm defining the surface, x squared plus y squared plus z squared equal 1, and also, see the comma there, the surface x equals 0, that's the plane of the board, that's the YZ plane. So if you look at my picture, you see a portion of a sphere, and you also see a portion of a plane there. So I defined two structures, plot structures, the portion of the sphere and the portion of the plane. That's why it's a set with the set braces. And then you have to, with implicit plot, you have to give limits on every variable you name. So x is something to something, y is something to something else, z is something to something else. Again, you can choose your axes, normal or box. When you turn the page, you'll see box axes. And you can put a title on. So this is problem 9 in the book. So there's a picture of a portion of a sphere and a portion of a plane. So here I've done it over. The only difference is I said axes equal boxed, and now I've used bigger, wider selection of limits on X, Y, and Z, if you notice. In the one we just did, X, Y, and Z were 0 to 1. Now they're -1 to 1, if you notice, and the boxed axes. So turn the page and see what you get. And you see the box, and you see because you're getting the bigger picture, what you have is the sphere and that plane sticking out in the corners that's cutting through it. The plane is actually there all the way through it, but what you see is where it sticks out, where the ears are, so to speak. And then I did it yet again, a different sphere. The 4 is the squared radius, so this one has radius 2 center at the origin. And I have a plane, but it's at an angle, see y equals x, and the boxed axes. And the maple will show you the sphere and the plane at the angle sticking out of the corners. Well, there is a maple package called vector calculus, and I finished the command with a semicolon there so that you'd see all the different commands that are possible, most of which we won't really work with. And then going on with that, we're talking about what's in tomorrow's class and next week. We're talking about multiplying vectors and the dot product and so on. So this first sheet of paper is as much of a maple as goes with what we have covered today. So hold on to the maple and bring it with you. We'll be working through this tomorrow and next week and so on. So come back